Fuel injection is a system for admitting fuel into an internal combustion engine. It has become the primary fuel delivery system used in automotive engines, having replaced carburetors during the 1980s and 1990s. A variety of injection systems have existed since the earliest usage of the internal combustion engine. The primary difference between carburetors and fuel injection is that fuel injection atomizes the fuel by forcibly pumping it through a small nozzle under high pressure, while a carburetor relies on suction created by intake air accelerated through a Venturi tube to draw the fuel into the airstream. Modern fuel injection systems are designed specifically for the type of fuel being used. Some systems are designed for multiple grades of fuel. Most fuel injection systems are for gasoline or diesel applications. Objectives: the functional objectives for fuel injection systems can vary. All share the central task of supplying fuel to the combustion process, but it is a design decision how a particular system is optimized. There are several competing objectives such as power output, fuel efficiency, emissions performance, ability to accommodate alternative fuels, reliability, drivability and smooth operation, initial cost, maintenance cost, diagnostic capability, range of environmental operation, engine tuning. The modern digital electronic fuel injection system is more capable at optimizing these competing objectives consistently than earlier fuel delivery systems. Carburetors have the potential to atomize fuel better. Benefits: driver benefits. Operational benefits to the driver of a fuel-injected car include smoother and more dependable engine response during quick throttle transitions, easier and more dependable engine starting, better operation at extremely high or low ambient temperatures, smoother engine idle and running, increased maintenance intervals, and increased fuel efficiency. On a more basic level, fuel injection does away with the choke, which on carburetor-equipped vehicles must be operated when starting the engine from cold and then adjusted as the engine warms up. Environmental benefits: fuel injection generally increases engine fuel efficiency. With the improved cylinder-to-cylinder fuel distribution of multi-point fuel injection, less fuel is needed for the same power output. Exhaust emissions are cleaner because the more precise and accurate fuel metering reduces the concentration of toxic combustion byproducts leaving the engine, and because exhaust cleanup devices such as the catalytic converter can be optimized to operate more efficiently since the exhaust is of consistent and predictable composition. History and development: Herbert Ackroyd Stewart developed the first device with a design similar to modern fuel injection, using a jerk pump to meter out fuel oil at high pressure to an injector. This system was used on the hot bulb engine and was adapted and improved by Bosch and Clessie Cummins for use on diesel engines. Fuel injection was in widespread commercial use in diesel engines by the mid-1920s. An early use of indirect gasoline injection dates back to 1902, when French aviation engineer Léon Levavasseur pioneered it on his Antoinette 8V aircraft powerplant. Another early use of gasoline direct injection was on the Hesselman engine invented by Swedish engineer Jonas Hesselman in 1925. Hesselman engines use the ultra-lean burn principle. Fuel is injected toward the end of the compression stroke, then ignited with a spark plug. They are often started on gasoline and then switched to diesel or kerosene. Direct fuel injection was used in notable World War II aero engines such as the Junkers Jumo 210, the Daimler-Benz DB601, the BMW 801, the Schwarzkopf 82FN. German direct injection petrol engines used injection systems developed by Bosch from their diesel injection systems. Later versions of the Rolls-Royce Merlin and Reiter 3350 used single-point fuel injection, at the time called pressure carburetor. Due to the wartime relationship between Germany and Japan, Mitsubishi also had two radial aircraft engines utilizing fuel injection, the Mitsubishi Kansei and the Mitsubishi Kasei. Alfa Romeo tested one of the very first electronic injection systems in Alfa Romeo 6E2500 with Alice Spessa body in 1940 Miglia. The engine had 6 electrically operated injectors and were fed by a semi-high-pressure circulating fuel pump system. Development in diesel engines: all diesel engines, with the exception of some tractors and scale model engines, have fuel injected into the combustion chamber. See diesel engines. Development in gasoline-petrol engines, mechanical injection. The invention of mechanical injection for gasoline-fueled aviation engines was by the French inventor of the V8 engine configuration, Léon Levavasseur, in 1902. Levavasseur designed the original Antoinette firm series of V-form aero engines, starting with the Antoinette 8V to be used by the aircraft the Antoinette firm built that Levavasseur also designed, flown from 1906 to the firm's demise in 1910, with the world's first V16 engine, using Levavasseur's direct injection and producing some 100 HP, flying an Antoinette 7 monoplane in 1907. The first post-World War I example of direct gasoline injection was on the Hesselman engine invented by Swedish engineer Jonas Hesselman in 1925. Hesselman engines used the ultra-lean burn principle and injected the fuel in the end of the compression stroke and then ignited it with a spark plug. It was often started on gasoline and then switched over to run on diesel or kerosene. The Hesselman engine was a low-compression design constructed to run on heavy fuel oils. Direct gasoline injection was applied during the Second World War to almost all higher-output production aircraft power plants made in Germany, the Soviet Union and the USA. Immediately following the war, hot rodder Stuart Heilborn started to offer mechanical injection for race cars, salt cars, and midgets, well known and easily distinguishable because of their prominent velocity stacks projecting upwards from the engine they were used on. The first automotive direct injection system used to run on gasoline was developed by Bosch, and was introduced by Goliath for their Goliath GP700 automobile, and Gutbrod in 1952. This was basically a high-pressure diesel direct injection pump with an intake throttle valve set up. This system used a normal gasoline fuel pump, to provide fuel to a mechanically driven injection pump, which had separate plungers per injector to deliver a very high injection pressure directly into the combustion chamber. The 1954 Mercedes-Benz W196 Formula One racing car engine used Bosch direct injection derived from wartime aero engines. Following this racetrack success, the 1955 Mercedes-Benz 300 SL, the first production sports car to use fuel injection, used direct injection. The same engine was used in the Mercedes-Benz 300 SLR famously driven by Stirling Moss to victory in the 1955 Mille Miglia. The Bosch fuel injectors were placed into the bores on the cylinder wall used by the spark plugs in other Mercedes-Benz six-cylinder engines. Later, more mainstream applications of fuel injection favored the less expensive indirect injection methods. Chevrolet introduced a mechanical fuel injection option, made by General Motors Rochester Products Division, for its 283 V8 engine in 1956. This system directed the inducted engine air across a spoon-shaped plunger that moved in proportion to the air volume. The plunger connected to the fuel metering system that mechanically dispensed fuel to the cylinders via distribution tubes. This system was not a pulse, or intermittent injection, but rather a constant flow system, metering fuel to all cylinders simultaneously from a central spider of injection lines. The fuel meter adjusted the amount of flow according to engine speed and load, and included a fuel reservoir, which was similar to a carburetor's float chamber. With its own high-pressure fuel pump driven by a cable from the distributor to the fuel meter, the system supplied the necessary pressure for injection. This was a port injection where the injectors are located in the intake manifold, very near the intake valve. During the 1960s, other mechanical injection systems such as Heilborn were occasionally used on modified American V8 engines in various racing applications such as drag racing, oval racing, and road racing. These racing-derived systems were not suitable for everyday street use, having no provisions for low-speed metering, or often none even for starting. However, they were a favorite in the aforementioned competition trials in which essentially wide-open throttle operation was prevalent. Constant flow injection systems continue to be used at the highest levels of drag racing, where full throttle, high RPM performance is key. Another mechanical system, made by Bosch called Jetronic, but injecting the fuel into the port above the intake valve, was used by several European car makers, particularly Porsche from 1969 until 1973 in the 911 production range and until 1975 on the Carrera 3.0 in Europe. Porsche continued using this system on its racing cars into the late 70s and early 80s. Porsche racing variants such as the 911 RS 2.7 and 3.0, 904/6, 906, 907, 908, 910, 917, and 935 all used Bosch or Cargo Fischer-built variants of injection. The early Bosch Jetronic systems were also used by Audi, Volvo, BMW, Volkswagen, and many others. The Cargo Fischer system was also used by the BMW 2000/2002 GE and some versions of the Peugeot 404/504 and Lancia Flavia. Lucas also offered a mechanical system that was used by some Maserati, Aston Martin, and Triumph models between 1963 and 1973. A system similar to the Bosch inline mechanical pump was built by Spyker for Alfa Romeo, used on the Alfa Romeo Montreal and on U.S. market 1750 and 2000 models from 1969 to 1981. This was designed to meet the U.S. emission requirements with no loss in performance, and it also reduced fuel consumption. Electronic injection. The first commercial electronic fuel injection system was Electrojector, developed by the Bendix Corporation and was offered by American Motors Corporation in 1957. The Rambler Rebel showcased AMC's new 327 Acclaim engine. The Electrojector was an option and rated at 288 bhp. The EFI produced peak torque 500 rpms lower than the equivalent carbureted engine. The Rebel owner's manual described the design and operation of the new system. The cost of the EFI option was $395 and it was available on June 15, 1957. Electrojector's teething problems meant only pre-production cars were so equipped, thus, very few cars so equipped were ever sold and none were made available to the public. The EFI system in the Rambler ran fine in warm weather, but suffered hard starting in cooler temperatures. Chrysler offered Electrojector on the 1958 Chrysler 300D, DeSoto Adventurer, Dodge D500 and Plymouth Fury, arguably the first series production cars equipped with an EFI system. It was jointly engineered by Chrysler and Bendix. The early electronic components were not equal to the rigors of underhood service, however, and were too slow to keep up with the demands of on-the-fly engine control. Most of the 35 vehicles originally so equipped were field retrofitted with 4-barrel carburetors. The Electrojector patents were subsequently sold to Bosch. Bosch developed an electronic fuel injection system, called D-Jetronic, which was first used on the VW 1600 TLE in 1967. This was a speed density system, using engine speed and intake manifold air density to calculate air mass flow rate and thus fuel requirements. This system was adopted by VW, Mercedes-Benz, Porsche, Citroën, Saab, and Volvo. Lucas licensed the system for production with Jaguar. Bosch superseded the D-Jetronic system with the K-Jetronic and L-Jetronic systems for 1974, though some cars continued using D-Jetronic for the following several years. In 1970, the Isuzu 117 Cooper copyright was introduced with a Bosch-supplied D-Jetronic fuel-injected engine sold only in Japan. In Japan, the Toyota Celica used electronic, multi-port fuel injection in the optional 18RE engine in January 1974. Nissan offered electronic, multi-port fuel injection in 1975 with the Bosch L-Jetronic system used in the Nissan L28E engine and installed in the Nissan Fairlady Z, Nissan Cedric, and the Nissan Gloria. Nissan also installed multi-point fuel injection in the Nissan Y44 V8 engine in the Nissan President. Toyota soon followed with the same technology in 1978 on the 4ME engine installed in the Toyota Crown, the Toyota Supra, and the Toyota Mark II. In the 1980s, the Isuzu Piazza, and the Mitsubishi Starion added fuel injection as standard equipment, developed separately with both companies' history of diesel-powered engines. 1981 saw Mazda offer fuel injection in the Mazda Luce with the Mazda FE engine, and in 1983, Subaru offered fuel injection in the Subaru EA81 engine installed in the Subaru Leone. Honda followed in 1984 with their own system, called PGM-FI in the Honda Accord, and the Honda Vigor using the Honda ES3 engine. The limited production Chevrolet Cosworth Vega was introduced in March 1975 using a Bendix EFI system with pulse-time manifold injection, 4 injector valves, an electronic control unit, 5 independent sensors and 2 fuel pumps. The EFI system was developed to satisfy stringent emission control requirements and market demands for a technologically advanced responsive vehicle. 5,000 hand-built Cosworth Vega engines were produced but only 3,508 cars were sold through 1976. The Cadillac Seville was introduced in 1975 with an EFI system made by Bendix and modeled very closely on Bosch's D-Jetronic. L-Jetronic first appeared on the 1974 Porsche 914, and uses a mechanical airflow meter that produces a signal that is proportional to air volume. This approach required additional sensors to measure the atmospheric pressure and temperature, to ultimately calculate air mass. L-Jetronic was widely adopted on European cars of that period, and a few Japanese models a short time later. In 1980, Motorola introduced the first electronic engine control unit, the ECIII. Its integrated control of engine functions is now the standard approach for fuel injection systems. The Motorola technology was installed in Ford North American products. Supersession of carburetors. In the 1970s and 1980s in the US and Japan, the respective federal governments imposed increasingly strict exhaust emission regulations. During that time period, the vast majority of gasoline-fueled automobile and light truck engines did not use fuel injection. To comply with the new regulations, automobile manufacturers often made extensive and complex modifications to the engine carburetor. While a simple carburetor system is cheaper to manufacture than a fuel injection system, the more complex carburetor systems installed on many engines in the 1970s were much more costly than the earliest simple carburetors. To more easily comply with emissions regulations, automobile manufacturers began installing fuel injection systems in more gasoline engines during the late 1970s. The open-loop fuel injection systems had already improved cylinder-to-cylinder fuel distribution and engine operation over a wide temperature range, but did not offer further scope to sufficient control fuel-air mixtures, in order to further reduce exhaust emissions. Later closed-loop fuel injection systems improved the air-fuel mixture control with an exhaust gas oxygen sensor and began incorporating a catalytic converter to further reduce exhaust emissions. Fuel injection was phased in through the latter 1970s and 80s at an accelerating rate, with the German, French, and US markets leading and the UK and Commonwealth markets lagging somewhat. Since the early 1990s, almost all gasoline passenger cars sold in first world markets are equipped with electronic fuel injection. The carburetor remains in use in developing countries where vehicle emissions are unregulated and diagnostic and repair infrastructure is sparse. Fuel injection is gradually replacing carburetors in these nations too as they adopt emission regulations conceptually similar to those in force in Europe, Japan, Australia, and North America. Many motorcycles still utilize carbureted engines, though all current high-performance designs have switched to EFI. NASCAR finally replaced carburetors with fuel injection, starting at the beginning of the 2012 NASCAR Sprint Cup Series season. System components, system overview, the process of determining the necessary amount of fuel, and its delivery into the engine, are known as fuel metering. Early injection systems used mechanical methods to meter fuel, while nearly all modern systems use electronic metering. Determining how much fuel to supply, the primary factor used in determining the amount of fuel required by the engine is the amount of air that is being taken in by the engine for use in combustion. Modern systems use a mass airflow sensor to send this information to the engine control unit. Data representing the amount of power output desired by the driver is also used by the engine control unit in calculating the amount of fuel required. A throttle position sensor provides this information. Other engine sensors used in EFI systems include a coolant temperature sensor, a camshaft or crankshaft position sensor, and an oxygen sensor which is installed in the exhaust system so that it can be used to determine how well the fuel has been combusted, therefore allowing closed-loop operation. Supplying the fuel to the engine, fuel is transported from the fuel tank and pressurized using fuel pump, S. Maintaining the correct fuel pressure is done by a fuel pressure regulator. Often a fuel rail is used to divide the fuel supply into the required number of cylinders. The fuel injector injects liquid fuel into the intake air. EFI gasoline engine components. Note: these examples specifically apply to a modern EFI gasoline engine. Parallels to fuels other than gasoline can be made, but only conceptually. Injectors, fuel pump, fuel pressure regulator, engine control unit, wiring harness, various sensors. Crank cam position, Hall effect sensor, airflow, MAF sensor, sometimes this is inferred with the MAP sensor, exhaust gas oxygen, oxygen sensor, EGO sensor, UEGO sensor. Engine control unit. The engine control unit is central to an EFI system. The ECU interprets data from input sensors to, among other tasks, calculate the appropriate amount of fuel to inject. Fuel injector. When signaled by the engine control unit, the fuel injector opens and sprays the pressurized fuel into the engine. The duration that the injector is open is proportional to the amount of fuel delivered. Depending on the system design, the timing of when injector opens is either relative each individual cylinder, or injectors for multiple cylinders may be signaled to open at the same time. Target air-fuel ratios. The relative proportions of air and fuel vary according to the type of fuel used and the performance requirements. See air-fuel ratio, stoichiometry, and combustion. Various injection schemes. Single-point injection. Single-point injection uses a single injector at the throttle body. It was introduced in the 1940s in large aircraft engines and in the 1980s in the automotive world. Since the fuel passes through the intake runners, it is called a wet manifold system. The justification for single-point injection was low cost. Many of the carburetor's supporting components such as the air cleaner, intake manifold, and fuel line routing could be reused. This postponed the redesign and tooling costs of these components. Single-point injection was used extensively on American-made passenger cars and light trucks during 1980 to 1995, and in some European cars in the early and mid-1990s. Continuous injection. In a continuous injection system, fuel flows at all times from the fuel injectors, but at a variable flow rate. This is in contrast to most fuel injection systems, which provide fuel during short pulses of varying duration, with a constant rate of flow during each pulse. Continuous injection systems can be multi-point or single-point, but not direct. The most common automotive continuous injection system is Bosch's K-Jetronic, introduced in 1974. K-Jetronic was used for many years between 1974 and the mid-1990s by BMW, Lamborghini, Ferrari, Mercedes-Benz, Volkswagen, Ford, Porsche, Audi, Saab, DeLorean, and Volvo. Chrysler used a continuous fuel injection system on the 1981 to 1983 Imperial. In piston aircraft engines, continuous flow fuel injection is the most common type. In contrast to automotive fuel injection systems, aircraft continuous flow fuel injection is all mechanical, requiring no electricity to operate. Two common types exist, the Bendix or SA system, and the TCM system. The Bendix system is a direct descent into the pressure carburetor. However, instead of having a discharge valve in the barrel, it uses a flow divider mounted on top of the engine, which controls the discharge rate and evenly distributes the fuel to stainless steel injection lines to the intake ports of each cylinder. The TCM system is even more simple. It has no Venturi, no pressure chambers, no diaphragms, and no discharge valve. The control unit is fed by a constant pressure fuel pump. The control unit simply uses a butterfly valve for the air, which is linked by a mechanical linkage to a rotary valve for the fuel. Inside the control unit is another restriction, which controls the fuel mixture. The pressure drop across the restrictions in the control unit controls the amount of fuel flow, so that fuel flow is directly proportional to the pressure at the flow divider. In fact, most aircraft that use the TCM fuel injection system feature a fuel flow gauge that is actually a pressure gauge calibrated in gallons per hour or pounds per hour of fuel. Central port injection. From 1992 to 1996, General Motors implemented a system called central port injection or central port fuel injection. The system uses tubes with poppet valves from a central injector to spray fuel at each intake port rather than the central throttle body. Fuel pressure is similar to a single-point injection system. CPFI is a batch fire system, while CSFI is a sequential system. Multi-port fuel injection. Multi-port fuel injection injects fuel into the intake ports just upstream of each cylinder's intake valve, rather than at a central point within an intake manifold. MPFI systems can be sequential, in which injection is timed to coincide with each cylinder's intake stroke. Batched, in which fuel is injected to the cylinders in groups, without precise synchronization to any particular cylinder's intake stroke. Or simultaneous, in which fuel is injected at the same time to all the cylinders. The intake is only slightly wet, and typical fuel pressure runs between 40 to 60 psi. Many modern EFI systems utilize sequential MPFI. However, in newer gasoline engines, direct injection systems are beginning to replace sequential ones. Direct injection. In a direct injection engine, fuel is injected into the combustion chamber as opposed to injection before the intake valve or a separate pre-combustion chamber. In a common rail system, the fuel from the fuel tank is supplied to the common header. This fuel is then sent through tubing to the injectors, which inject it into the combustion chamber. The header has a high-pressure relief valve to maintain the pressure in the header and return the excess fuel to the fuel tank. The fuel is sprayed with the help of a nozzle that is opened and closed with a needle valve, operated with a solenoid. When the solenoid is not activated, the spring forces the needle valve into the nozzle passage and prevents the injection of fuel into the cylinder. The solenoid lifts the needle valve from the valve seat, and fuel under pressure is sent in the engine cylinder. Third-generation common rail diesels use piezoelectric injectors for increased precision, with fuel pressures up to 1,800 bar or 26,000 psi. Direct fuel injection costs more than indirect injection systems. The injectors are exposed to more heat and pressure, so more costly materials and high-precision electronic management systems are required. Diesel engines. Most diesel engines have fuel injected into the combustion chamber. Earlier systems, relying on simpler injectors, often injected into a sub-chamber shaped to swirl the compressed air and improve combustion. This was known as indirect injection. However, this was less efficient than the now common direct injection, in which initiation of combustion takes place in a depression in the crown of the piston. Throughout the early history of diesels, they were always fed by a mechanical pump with a small separate chamber for each cylinder, feeding separate fuel lines and individual injectors. Most such pumps were inline, though some were rotary. Most modern diesel engines use common rail or unit injector direct injection systems. Gasoline engines. Modern gasoline engines also utilize direct injection, which is referred to as gasoline direct injection. This is the next step in evolution from multi-point fuel injection, and offers another magnitude of emission control by eliminating the wet portion of the induction system along the inlet tract. By virtue of better dispersion and homogeneity of the directly injected fuel, the cylinder and piston are cooled, thereby permitting higher compression ratios and earlier ignition timing, with resultant enhanced power output. More precise management of the fuel injection event also enables better control of emissions. Finally, the homogeneity of the fuel mixture allows for leaner air-fuel ratios, which together with more precise ignition timing can improve fuel efficiency. Along with this, the engine can operate with stratified mixtures, and hence avoid throttling losses at low and part engine load. Some direct injection systems incorporate piezoelectronic fuel injectors. With their extremely fast response time, multiple injection events can occur during each cycle of each cylinder of the engine. Swirl injection. Swirl injectors are used in liquid rocket, gas turbine, and diesel engines to improve atomization and mixing efficiency. The circumferential velocity component is IRST generated as the propellant enters through helical or tangential inlets, producing a thin, swirling liquid sheet. A gas-I-led hollow core is then formed along the center line inside the injector due to centrifugal force of the liquid sheet. Because of the presence of the gas core, the discharge coefficient is generally low. In swirl injector, the spray cone angle is controlled by the ratio of the circumferential velocity to the axial velocity and is generally wide compared with non-swirl injectors. Maintenance hazards. Fuel injection introduces potential hazards in engine maintenance due to the high fuel pressures used. Residual pressure can remain in the fuel lines long after an injection-equipped engine has been shut down. This residual pressure must be relieved, and if it is done so by external bleed-off, the fuel must be safely contained. If a high-pressure diesel fuel injector is removed from its seat and operated in open air, there is a risk to the operator of injury by hypodermic jet injection, even with only 100 psi pressure. The first known such injury occurred in 1937 during a diesel engine maintenance operation. Notes. Further reading, Patents, U.S. Patent 3,430,616 a Euro Fuel Injection Control System a Euro Autoglap Paragraph CKLER, AL. U.S. Patent 3,500,801 a Euro Actuator Circuit for Electronic Precision Fuel Metering Systems a Euro E. David Long and Keith C. Richardson, U.S. Patent 3,504,657 a Euro Cold Start Fuel Enrichment a Euro Dieter Eichler, al. U.S. Patent 3,548,791 a Euro Precision Fuel Metering. A Euro E. David Long, U.S. Patent 4,069,795 a Euro Startup Control for Fuel Injection System a Euro E. David Long and Keith C. Richardson, external links. History of the D-Jetronic System, High Quality Fuel System Repairs Guide, How Fuel Injection Systems Work.